Thank you everyone for tuning in. This is a short summary of our paper, Individualized Privacy Accounting via Subsampling with applications in Combinatorial Optimization. And this joint work with Buddy Kasi, British Kamat, Ravi Kumar, Adam Silfon, and all of us are from Google Research. We are interested in privacy preserving algorithm under the notion of differential privacy. Just to recall, there is a sensitive dataset. We run some algorithm M on it and we get the output. We say that the algorithm M satisfies epsilon delta differential privacy, or epsilon delta DP for short, if when we consider two input dataset X and X prime, such that X results from adding or removing a single record from X prime, then the probability that any event occur in the output Mx is at most e to the epsilon times the same probability on Mx prime plus delta. The smaller epsilon and delta are, the more private the algorithm. When delta is equal to 0, we say that the algorithm satisfies PLDP. And when delta is greater than 0, we call it approximate DP. Typically, we prefer PLDP over approximate DP because approximate DP allows for some catastrophic privacy violation event with small probability. For example, an algorithm that released the entire dataset in the clear with probability delta would still satisfy approximate DP, but not pure DP. Combinatorial optimization problems have long been studied in conjunction with differential privacy. Interestingly, however, for many of these combinatorial optimization problems, only approximate DP algorithms are known with good bounds. These include fundamental problems such as set cover, submodular maximization, and clustering problems like k-means and k-median. This raise a natural question of whether we can get similar algorithms but with pure DP instead of approximate DP guarantee. And this brings us to our main contribution. We give a generic recipe to make previously approximate DP algorithms into PLDP ones. For combinatorial optimization, we obtain PLDP algorithms for problems like set cover, submodular maximization, and k-means and k-median, where the approximation ratio and additive error essentially match and sometimes even improve the previously known bound, while also achieving PLDP instead of approximate DP. We also have more results in the paper that I will not discuss in this summary. We will now dive into more details on how we arrive at these results. As our paper's title suggests, we will use subsampling procedure. So recall that in subsampling, instead of running the algorithm on the dataset directly, we sample each user independently with probability p to get a subset of the original dataset. And then we run our algorithm on this subsample dataset instead. This, by now, a well-known phenomenon that subsampling makes an algorithm more private. In particular, in the context of DP, if we run the epsilon DP algorithm on top of this subsampling, then the epsilon will decrease by a factor of roughly p. However, this doesn't solve our problem yet, since we still need the original algorithm to be PLDP in order to get the final guarantee to be PLDP. So we will need a new amplification by subsampling theorem for our purpose. And to describe this new theorem, we also need a slight modification of differential privacy. Recall that in the standard differential privacy notion, we consider x and x prime such that x is a result of adding or removing a single record from x prime. Now we will consider the one-sided variant of this notion called one-sided DP, where we now only enforce the inequality for x that is a result of adding a record from x prime. In other words, we allow this inequality to be violated for x that is a result of removing a record from x prime. To avoid confusion, we will call the original notion of DP two-sided DP henceforth. Our amplification by subsampling theorem can now be stated as follows. If we take a one-sided DP algorithm and applying subsampling on top of it, then it becomes two-sided DP. So the picture is exactly the same as before, except that we don't require the original algorithm to be two-sided DP. We only require it to be one-sided DP. This gives us an advantage, for example, for the combinatorial optimization problems, since it means that it suffices for us to give a one-sided DP algorithm for the problem, since anyway we can apply the subsampling on top of it afterwards and get a two-sided DP algorithm. So how do we come up with the one-sided DP algorithms? It turns out that most algorithms considered in literature are already one-sided DP. Just to give you an example, let's consider the submodular maximization problem. So in the submodular maximization problem with cardinality constraint, we are given as input an integer k, a dataset x, and for each record x, we have a monotone submodular function fx. The goal is to output a subset of size k of the universe that maximizes the sum of fxs. Without the privacy constraint, there is a relatively simple greedy algorithm for the problem. We start with an empty set, and we repeat the following process k time. We pick the element that maximizes the marginal gain and add it to the set, and we just return the set at the end. So this algorithm gives 1 minus 1 over e approximation in the non-private setting. To make this algorithm satisfy differential privacy, Gupta et al. Proposed that when we try to find the u that maximizes the marginal gain, we use the epsilon naught dp exponential mechanism. Since each iteration is epsilon naught dp, we can apply the basic composition theorem for differential privacy to conclude that the entire algorithm is k times epsilon naught dp. Surprisingly, Gupta et al. Gives an elegant proof that shows that this increase of k is not necessary if we allow for approximate dp. In particular, they show that the epsilon only increases by a factor of log 1 over delta, regardless of the number of iterations k. And this result is for two-sided dp. Our observation here is that this algorithm already satisfies epsilon naught one-sided dp, so we can apply this together with our amplification by subsampling theorem and gets the result that we claimed earlier. And that's essentially the entire proof for submodular maximization problem. The results for the other problems are fairly similar as well. So just to summarize here, we give new PODP algorithms for combinatorial optimization using a simple but powerful observation that subsampling makes one-sided DP algorithm into two-sided DP one. Given this, it suffices to give one-sided DP algorithms, and we observe that the algorithms that have been used in literature, including the repeated exponential mechanism that we just discussed, and also the repeated above threshold mechanism, already satisfy one-sided DP. So we really don't have to do anything new here. In terms of open problem, to satisfy one-sided DP, we require certain monotonicity constraint. It would be interesting to see whether our technique can work without monotonicity. So that's all that I have time for today. If you want to learn more about our paper, please visit our poster at ICML 2024 or check out our paper, which is on arXiv. Thank you very much.